Hi, I'm Hilary Watt from Imperial College London. Hypothesis tests, what are they? And p-values, how do we interpret them? This is looking at two sample t-tests comparing mean between two different groups. And apply to the example comparing mean BMI between men and women. Informally, could mean differences this large readily occur by random chance alone? The principles underlying this is the fact that when we do research, we're not specifically interested in our study participants, but we're wanting to generalise our conclusions to some broader populations. And what we do is we assume random sampling of study participants from the population. And we use this as a way of accounting for random chance in our results. We set up a null and an alternative hypothesis. The null, that there's no difference in population mean BMI between men and women, and the alternative is that there is a difference in population mean between men and women. The first step is to actually look at your data and see what the distributions like in men and women and to compare them. We know BMI in all our study participants because we've measured and calculated it, and therefore we know the mean BMI in men and the mean in women and the difference between them, which is 0.32 higher in men. And we can also work out the standard deviations, which is around about 5, a little bit less in men and more in women. Then most people with a normal distribution are going to lie within around about 2 standard deviations of the mean, between about 18 and 38. Although some are going to be further outlying than that. The sample size is around about 1,500 in each. And what you can see is there's a very substantial overlap in the distribution of BMI between the two genders, and so there really isn't all that much difference between them. The difference in mean, 0.32, is very much smaller compared to the spread of BMI in each gender. Now we have to remember what we were actually interested in, the difference in mean in the population that we are selected our study participants at random from, and we can only estimate it. And we estimate it using the difference in mean amongst our participants. And then we acknowledge that there's some imprecision. We measure the precision of this estimate using the standard error of the difference. That's calculated based on the standard deviations and sample sizes in both groups. When you've got a larger sample size, you've got higher precision and a smaller standard error, much smaller than standard deviation. The standard error in this case is 0.18. Now you can work out the Z value, which is calculated as the difference in participants means over the standard error of the difference. And another way of saying that is the difference in participants mean is used to estimate the difference in population mean. And the standard error is the precision of this estimate. So the Z value is a ratio of this estimate to its precision. And in this case, it's 0.32 divided by 0.18, it's 1.81. You can look up the Z value along the horizontal axis of the graph shown and go upwards and then across to the left to find a p-value of 0.07. The way to interpret that is weak. On the graph, it's got the word weak, so this is a weak suggestion of possible difference in mean BMI by gender. On the other hand, if you had a very much larger Z value of 3.61, you can again look at that on the horizontal axis, find that value, go upwards and then across to the left, and to get a p-value of 0.003, and this is very strong evidence of a difference in population mean by group, if the Z value was that much bigger. The idea of this graph is to give you some intuitive feel for the link between the Z value and the p-value, and the fact that the Z value is a ratio of an estimate to its precision, and that links to the p-value. And according to how small the p-value is, you get stronger and stronger evidence for population differences in means. So it's partly to discourage people focusing specifically on one particular cutoff and p-values such as 0.05, and to give an intuitive understanding for what it all means. Of course, in practice, you're going to use software to calculate your p-values because you can't calculate them at all precisely from this graph. This is further information on interpreting the p-value. So define the p-value. First of all, we assume the null hypothesis is true, or more specifically, we assume no difference in population mean BMI by gender. And then the probability of getting a mean BMI at least this large or larger in the sample is 0.07. And what we conclude, it's not that unusual. 7% chance of getting a difference in this big or bigger, assuming the null hypothesis is true. And so data are compatible with the null hypothesis being true, which we can say null hypothesis might plausibly be true. Data are compatible with being selected at random from a population where mean BMI doesn't differ by gender. Informally, differences in mean of this size could readily be seen by random chance alone. But I did say, rather than relying on the 0.05 cutoff, it's quite good to acknowledge that p-values are continuous. So maybe because it's quite near the cutoff, it's not so highly compatible. It's not like really highly compatible with being selected at random chance with selection from a null hypothesis from a population where they aren't associated. So you might say there's a weak suggestion of possible difference in population mean BMI by gender. On the other hand, we now have a much smaller p-value, so how would we interpret this? So again, the definition of the p-value, assuming no difference in population mean by gender, probability of getting a difference in sample means at least this large is only 0.003, it's 0.3%. So if you, just by random chance, you could get a difference in mean this big, but it'd be really quite a fluky result, so it'd only happen really occasionally. And therefore you can legitimately conclude data are not readily compatible with being selected at random in a population where mean BMI doesn't differ by gender. We can reject the null hypothesis and conclude the population mean is higher in men. You do have to remember to make absolutely sure you know which gender has got the higher mean BMI. It's not actually that useful simply to conclude it's different. And because the p-value is less than 0.001, we can conclude we've got very strong evidence that population mean BMI is higher in men. So informally, mean differences of this size could not readily be seen by random chance alone. When you're interpreting the p-value, you should really only interpret them in the context of the data. So, as I said, you've got a really broad overlap of the distributions. If the sample sizes were 4 times as big, the standard error is half the size, the z value is twice as big, and that's how you can end up with a p-value of 0.003. So you could get a p-value of 0.003 even with distributions that overlap this much. And so then you could have really strong evidence for a difference in mean, but the question is, do you care, or is it this difference in mean is so small that it's negligible? So that's a separate consideration. And obviously, if it's really, really big difference in mean, then you interpret it very much different in terms of clinically what its implications are compared to a tiny difference in mean. So it's really, really important to consider that as well. On the other hand, if you've got tiny sample size, then you might have p is greater than 0.05, and that might really be saying, well, you don't really know much. It could be compatible with random chance, but you've got really tiny sample sizes, so we don't really know if the populations have got different means. Limitations on p-values, as I say, only meaningful assessed alongside differences in means and preferably confidence intervals on those differences in means as well. They assume random sampling of study participants' populations, so that in some senses then they're biased if participants are not representative of the population we're wanting to generalise to. It's very rare that you get true random sampling from a population. And even if you do surveys, which occasionally they do sometimes attempt random sampling, but of course there's going to be a certain amount of non-response or people that aren't on the registers, so that can cause a little bit of bias. They don't account for any biases in measurement, and particularly any differential bias between men and women would be an issue. If they measured men and women in their shoes, and women are more often wearing high-heeled shoes, that would cause a bias in height measurements. A differential bias between men and women. You also have to remember, if you get a statistically significant result, like a small p-value, except really good evidence for a population difference in mean, it might only apply to the particular setting where the research was done. So it might apply to one particular country, one particular age range, and it isn't necessarily generalisable beyond that. T-tests, people say they assume the normal distribution of measurements. In practice, this doesn't really matter all that much, particularly with for large sample sizes. Strictly speaking, what you want is a normal distribution of the distribution of study means, and because of the central limit theorem, with big sample sizes, even with really weird distributions, I mean, this is a bit of a technical aside, but in practice it doesn't matter too much the assumption of normality of measurements, although it does matter somewhat more with smaller sample sizes. But in practice, in exams and in the published literature, people do tend to expect you to base t-tests on the assumption that the normal distribution should be met. Now I'm going to acknowledge that there's actually two different versions of the two-sample t-test, one that assumes the same standard deviations in both groups and one that doesn't. Overall p-values, they assess the compatibility of our data with random selection from a population where mean BMI doesn't differ by gender. The ASA statement on p-values, that was designed to up the standard of p-values because of concern that they can be poorly interpreted in the literature, and that was really encouraging the use of compatibility in these interpretations. And they also emphasise interpreting them alongside estimates of the effect size and other considerations such as the study design, potential possible bias. And so there's a lot of different things that should feed into what appropriate scientific conclusions you make. So this is Hilary Watt talking about p-values and how you interpret them with a two-sample t-test. I've also got a video on confidence intervals that you might want to see, and a science video. And if you subscribe to my channel, I'm going to be putting up some more science comedy videos and teaching videos. Thank you very much.